We have seen an application of gradient in calculating the directional derivative of a scalar valued function of several variables. Okay. Next, we are going to see two more applications of the gradient vector. The gradient vector can be used to calculate the or find the normal vector to a given curve. First, we will see how to find the normal vector to a plane curve. So here, we taken a curve y equal to x square. For such an equation, y equal to f of x can be always written as y minus f of x equal to 0. For example, y equal to x square can be written as y minus x square equal to 0, right? So my curve I am taking to be of the form f of x comma y equal to 0. It's a relation connecting y and x, so it represents a curve. Okay, so how to find the normal vector to this curve? What is the normal vector to this curve? It's a plane curve. So in the plane, you select a point here. So at this point, there is a tangent vector which is along the direction of the curve. This is the tangent vector here in that orange color. And the vector which is perpendicular to the tangent vector is called the normal vector. So we want to find both t bar as well as n bar. So here first we'll find what is n bar, and then we'll use that n bar to find the tangent line. Okay. So the idea is this. So we have considered f of x comma y equal to 0 along this curve. For every point on the curve, on this curve, will satisfy the equation f of x y equal to 0, or this is a level curve. Basically, it is f inverse of 0. Okay. Now, as I said, the points on a curve can be treated as a function of time or function of the arc length also. So I consider it as a function of x arc length, x of s comma y of s. So you can treat this x as x of s and y as y of s if you are describing this curve using arc length. So this equation f of x y equal to 0 can be taken as f of x of s comma y of s equal to 0. In that case, what happens is f is a function of x as well as y, and x is again a function of s, y is also a function of s. So since f is equal to 0 on the curve, for every point on the curve, we'll have f of xy equal to 0, and f is ultimately a function of s. So we know that if f equal to 0, df by ds is equal to 0. Okay, but df by ds using chain rule, you can say that it is dou f by dou x into x dash s plus dou f by dou y into y dash s. So we'll get fx into x dash s plus fy into y dash x equal to y dash s equal to 0. In terms of gradient, you can write it as fx comma fy dot product with the x dash s comma y dash s equal to 0. So this is the gradient of f at this point, the point we are taking. Suppose this is x naught y naught, then this is del f at x naught y naught dot product with the what is x dash s comma y dash s, that is nothing but r bar dash s, right? R bar dash s, but we have seen that, so this is equal to 0. The dot product of del f and r bar dash s is equal to 0. So you can say that we have already seen that this tangent vector t bar is nothing but r bar dash s in terms of arc length. Tangent vector is nothing but the derivative of the curve in terms of the arc length. So what you have obtained is del f dot t bar is equal to 0. That says that del f and t bar are perpendicular to each other. So if this is del f, then t bar will be 90 degree to that. So this angle will be always 90 degree. So what it says is this del f vector is perpendicular to t bar vector, means if this is t bar direction, the del f direction will be either this or this, right? So it's giving you the normal direction. So n bar vector, the normal vector is parallel to del f direction, or you can say that the gradient vector is always in the normal direction to a curve. So if this is a curve, then the gradient at this point will be this vector. Okay, or it can be also this vector. So n bar is equal to del f. N bar is a unit vector. So n bar is nothing but del f divided by length of del f, norm del f. Okay. So this is how we can calculate the unit normal vector using the gradient equation. For example, if you consider y equal to x square as a function, and mm, uh, so you can write it as y minus x square equal to 0. Okay. So f of x y is equal to constant is also okay. Like constant is sufficient. So here we are getting that constant as 0. So this you take as f. F is equal to y minus x square. So you calculate what is fx. Fx is nothing but minus 2x. And what is fy? Fy is equal to 1. All right. So at a point, at a fixed point on the curve y equal to x square, for example, this 2 comma 4 is a point on the curve y equal to x square. So at 2 comma 4 your fx value is going to be minus 2 into 2, that is minus 4, and fy value is going to be 1. So the del f vector is going to be at the point 2 comma 4 is nothing but minus 4 comma 1, minus 4 comma 1. Okay, so this will be giving you the normal vector at the point 1 2 comma 4. So at that particular point 2 comma 4, the normal direction, normal vector can be taken as minus 4i plus 1j, minus 4i plus 1j. And the unit normal vector, that is n cap, can be taken as this minus 4i plus 1j divided by its length. What is the length? Length is root of 16 plus 1, so root 17. Okay, so this is how we find the normal vector and unit normal vector in the case of a plane curve. Now let us find the equation of the tangent line. So normal vector we have found n cap. Normal vector is del f will give you the normal vector, and the tangent vector will be perpendicular to the normal vector, that is at 90 degree, right? This angle will be 90 degree. And what I'm trying to do is I'm trying to write the equation of the tangent line. Tangent line is a infinite line, and we want to write the equation of the line. Every equation of lines can be written as y equal to mx plus c in the plane, right? So here what I'm trying to do is the point at which we are finding this del f. Del f is evaluated at x naught comma y naught, where x naught comma y naught is a point on the curve. For example, 2 comma 4 we have taken a point, right, in the example which I gave for this function. That is y equal to x square. We have taken the point as 2 comma 4. Like that, at a fixed point only, we are trying to find the tangent line. So for finding the equation of the tangent line, you take an arbitrary point x comma y on the tangent line. Then what you know is this line connecting this x naught, y naught, and x comma y. X comma y can be there or any point on this line. Okay. So, but you know that the line connecting this x comma y with x naught, y naught, that particular vector is going to be perpendicular to del f vector. So we have this x minus x naught comma y minus y naught is perpendicular to del f vector. That means this x minus x naught I plus y minus y naught j, which is this particular line, this line segment, is x minus x naught I plus y minus y naught j. It is perpendicular to del f means fxi plus fyj. That means their dot product must be 0, right? So what is the dot product? Fx into x minus x naught plus fi into y minus y naught. That should be equal to 0. So for any x comma y on this tangent line, it should satisfy the equation fx at x naught y naught into x minus x naught plus fy at x naught y naught into y minus y naught equal to 0. And that is the equation of the tangent, not tangent plane, tangent line, because there exists only one line, right? Tangent plane will happen for 3D curves. We'll see next what happens when you consider a 3D curve. Okay.